Hi, everyone. We worked on the data set that predicts the probability of an individual having heart disease based on a set of data. My name is Yim Fong, and I did the project with Hala and Claire.
Okay, so the data set that we picked is a heart disease prediction data set where there was data collected on commonly known risk factors of heart disease within a sample of people. And then with the risk factors in that sample of people, the data was collected on whether or not the heart disease actually ended up being present. So our motivation for choosing this data set was that heart disease is very prevalent. It's the #1 killer, both in the US and worldwide. So it's definitely prevalent in the world, and it's something that has been killing people and has been a problem for a very long time. And even now, with the presence of COVID, heart disease is still the #1 cause of death in the world and the US. But due to the prevalence of COVID, it's kind of less talked about and somewhat overlooked. So we wanted to just take a look at that data a bit more closely. So the background for this data set is that the file describes several risk factors of heart disease as the predictor variables for the singular response variable of presence of heart disease. So we have multiple predictor variables and one response variable. So the predictor variables that we had in this set were age, sex, chest pain type, including atypical angina, non-anginal typical angina, and asymptomatic, which means there's no chest pain known to the patient. And then we have resting blood pressure, cholesterol, fasting blood sugar, which is just based on low and high, and 0 or low would be regular. So fasting blood sugar, if it was 0 in the original data set, that means that it was regular, and 1 would be high. Resting electrocardiogram, which is the ECG, max heart rate, exercise angina, old peak, which is the highest ST slope, which is the last variable, ST slope, which is segment shifts induced by exercise. So old peak would be the largest shift in slopes induced by exercise. So in order to prepare the data, we got rid of some of the more arbitrary measures, more arbitrary predictor variables. So fasting blood sugar, ST slope, and old peak were filtered out, as these ones aren't really as indicative of heart disease as the other factors were, and we wanted to focus kind of on the main risk factors that are present for heart disease. So we also changed the resting electrocardiogram variables from normal LVH and ST, because ST just means like a flat abnormal section. So we change it to normal LVH and abnormal because that's a bit more readable to the general viewer. And that's how we decided to change that. So the predictor variables now are just going to be age, which is numeric, sex, which is categorical, only male or female, resting blood pressure, which is numeric, chest pain type, which is categorical, cholesterol, which is numeric, resting ECG with the new variables that we talked about above, and max heart rate, which is once again numeric. So looking at kind of the spread of the numeric variables, we took a look at the range and the mean and standard deviation. So with age, we have a large range. We're going all the way from 28 to 77, but the mean is 53.51, so about 54 years old. So we're kind of looking at middle-aged people around average. The resting blood pressure, we have a range of 80 to 200. We have about 80 to 200, and then the resting blood pressure average is about 132, which is slightly high, even though we have people on the lower range at 80. And then we have cholesterol, which once again is a huge range from 0 to 603.3. But even with that very large range, and a lot of people, and some people at 0 even, the cholesterol is still a bit high at almost 200. The max heart rate goes from 60 to 202, and the average is about 136.8, which is above average. That is a bit of a higher heart rate than normal people's resting heart rate. So then the categorical variables summary, we looked at each categorical variable and whether it resulted in the presence of heart disease or not. So we're definitely seeing a lot more data collected on males than we are on females in this set. So that's the first thing to notice. The second thing is that we're seeing a lot of people with a normal ECG. So the electrocardiogram is not always showing some abnormal spikes and slopes and things like that. And then we have the last categorical variable of chest pain type, which is asymptomatic, atypical angina, and non-angina and typical angina. So we're not really seeing a lot of people with typical, but and nor a lot of data collected on them, but a lot of people who are asymptomatic and don't really feel chest pain still have heart disease. And that's what we're seeing in this chart mainly. And then lastly, we made some charts just to put all of the categorical variables together to see kind of the spread of how things work. So we see a lot of people are up in the asymptomatic area. We have a lot of people in non-anginal as well. And then atypical angina and typical angina are, we're not seeing as many people in that data set. So it's a bit less prevalent. And those are our categorical variables.
Okay, so this next part is data visualization. The first graph is a bar graph, which displays how many patients in the data set have heart disease and how many do not. There are about 100 more patients with heart disease than without in this data set. The next bar graph displays the distribution of males versus females in this data set. And as shown, there are around 400 more males included in this data set than females. And this large difference is important to note because it could skew some of the data which revolves around male or females. This next bar graph displays the distribution of chest pain type. There are 4 different kinds, and it appears that asymptomatic is the most common by far. Non-anginal is the second most common. Atypical angina is the third most common, and typical angina is the least common. This next graph is a stacked bar graph, which is similar to the last one. However, this one displays the distribution of males and females within each category. This is a histogram which displays the distribution of resting blood pressure among the patients in the data set, and the range spreads from roughly 100 through 200. The most common resting blood pressure appears to be around 125. This histogram is skewed to the right and is unimodal. This side-by-side box plot shows the relationship between resting ECG and max heart rate, and it appears that abnormal LVH and normal ECGs are all roughly normally distributed, and normal and LVH seem to be associated with higher maximum heart rate than abnormal ECG. They also seem to have a wider distribution than the abnormal, as that one is more condensed, and the outliers of this data set are displayed by the pink dots. As you can see, the abnormal box plot has the lowest interquartile range, so it is more condensed than the others, but it also has the most outliers. And the normal box plot has the largest overall range. This box plot shows the relationship between heart disease and max heart rate. The max heart rate for a person without heart disease, shown on this data, is clearly higher than that of a person with heart disease. The box plot of the group without heart disease is normally distributed, while the box plot of the group with heart disease is skewed right, with the data more condensed on the lower end. The box plot predicts that one with a higher max heart rate would be less likely to have heart disease. So this scatter plot displays that there's no true correlation between max heart rate and cholesterol level. The correlation function found that this correlation was 0.24, which tells us that there really is no strong correlation here, as a strong one would be 1 or -1, close to that. Okay, so this next one is a bubble plot, which displays that there is no correlation between cholesterol, resting blood pressure, age, and chest pain type. The size of the bubbles is determined by the age of the patient, and the color is determined by the chest pain the patient has. This bubble plot is pretty similar to the one before, however, with the one difference that heart disease is categorized by color. The blue dots indicate that the person does have heart disease, and the red dots indicate the person does not have heart disease. So on this plot, it displays that low max heart rate is a predictor for heart disease. As you can see, more blue bubbles are on the left side, where the lower max heart rate is, while more red are on the right, which make up the higher max heart rate area. And resting blood pressure seems to not be as strong of a predictor of heart disease as shown here. This one is a heat map, and it displays chest pain type in relation to sex and age. And according to the map, it seems as though males experience atypical angina and typical angina chest pain earlier on than females do, while both sexes experience asymptomatic and non-angina chest pain around the same age. However, the data may be skewed since there's a larger proportion of men than women in this data set.
We conducted 1 sample and 2 sample inferences on the data set. We used a 95% confidence interval to find the average cholesterol of people between ages 28 and 77, as this was our population of focus. We used a 95% confidence interval, and we are 95% confident that the average cholesterol level of people between the ages of 28 and 77 is between 192 and 206 milligrams per deciliter. We also did a 2 sample t-test to predict and compare the maximum heart rate between males and females. The null hypothesis is that the average maximum heart rate for males and the average maximum heart rate for females is equal. And the alternative hypothesis is that the average maximum heart rate for males is unequal to the average maximum heart rate for females. And we used a significance level of 0.01. The average maximum heart rate for females is about 146, and the average maximum heart rate for males is 134.33. Since the p-value is almost 0 and is significantly less than the significance level of 0.01, we reject the null hypothesis that the average maximum heart rate for males is equal to the average maximum heart rate for females. From that, we are 95% confident that the average maximum heart rate for females is between 8.15 and 15.47 beats per minute greater than the average maximum heart rate for males. Additionally, we conducted a simple linear regression, and using linear regression, we found that the correlation between age and maximum heart rate is negative 0.38. So this is a weak negative relationship between age and maximum heart rate. The model is maximum heart rate is equal to negative 1.105 age plus 257.925. Therefore, this model shows that for every increase in age by 1 year, maximum heart rate on average decreases by about 1.1 beat per minute. Additionally, we conducted multiple regression. Using multiple regression, the model predicts that if resting blood pressure is held constant and the maximum heart rate is predicted to decrease by about 1.5 beats per minute for every year that someone ages. The model also predicts that if the age is held constant, the maximum heart rate is predicted to increase by 0.7905 beats per minute for every 1 millimeter of mercury increase in resting blood pressure. From the multiple R-squared value, we found that 2.58% of the variation in maximum heart rate is due to age and resting blood pressure. The predictive power of this model is 2.58%, and the model predicts that maximum heart rate is equal to negative 1.4996 times age plus 0.7905 times blood pressure plus 174.3918. Finally, for logistic regression, we predicted the model shown below, and if we plugged in the variable shown here, so if age was 80, resting blood pressure was 120 millimeters of mercury, cholesterol was 250 milligrams per deciliter, and maximum heart rate was 120 beats per minute. This individual has about an 80.5% chance of having heart disease. Okay, thank you for watching, and I hope you enjoyed our presentation of the data set on heart disease predictors.